Lecture of the year. For those of you who don't know me, my name is Abby. I'm the Academic Events Coordinator for the Maxwell Society. We understand there's a lot of new undergrads, postgrads, PhDs, staff that might be in the room today, so welcome to things. Welcome to the Physics Department and welcome to Maxwell Lectures. For those of you who don't know, the Maxwell Lectures have been running since the 1950s and have been a staple of the Physics Department. This is the first year that the Maxwell Society is taking full responsibility for the organisation of these lectures, and we're really excited to introduce you to the speaker arrangement for the year. We're starting out, of course, with Professor Sean Carroll of Caltech. When looking at how to introduce such a physicist, I went to his website, preposterousuniverse.com, thought I would get some information by having a little look around at all these things. So I thought, let's start with the CV. 17 pages later, I realized that I do not have enough time to go through the level of work that he has been involved in. So from his work in his own research to consultancy, to TV and film, to his own books that he's written, and he's one of the leading scientists of our time, and we are extremely proud to have him today. So, ladies and gentlemen, please join me in welcoming Professor Sean Carroll.
My understanding is that this is the first lecture of the year to the Maxwell Society Undergraduate Physics Society. My job is to scare you off from pursuing a career in physics, which I think I can do in the short time that I have here. There's actually, I'm going to try to sneak in 2 talks in the hour that we have here. 2 short talks rather than one long one. They're connected. For the first half, I'm going to give you a sales pitch for something called the ManyWorlds Interpretation of quantum mechanics, which you've all heard of before. Some of you may love, some of you may hate. I'm going to try to explain both why it's something you should love, but also even more importantly, why it really matters that we think about the foundations of quantum mechanics in the way that we often don't. And in the second half, I'm going to put some of that stuff to use in moving right to the cutting edge of modern physics and thinking about quantum gravity and the emergence of space-time. Why understanding quantum mechanics is going to be very important in that task. So as you can see, I have many collaborators, students, and postdocs at Caltech who are extraordinarily helpful in some of the work I'll be describing. So, for those of you who haven't yet started your physics classes in earnest, before there was quantum mechanics, there was classical mechanics. There was this guy, Isaac Newton, who invented classical mechanics. And it was a very simple theory. You might not believe that if you're going through your first year courses. But the theory itself is extremely simple. There's 2 things that are involved in a classical mechanical theory. There is the state of a system. That is a point in phase space, as we define it, which means the position and the velocity, or the momentum, of every part of the system. So if you have a ball and you tell me where it is and how fast it's moving, Newtonian mechanics will tell you where it's going to go. You don't need to know the acceleration or the time of day or other pieces of information. Just the state of the system. And then there are equations of motion, which will tell you how to go from one point in phase space to the next one. It was this guy, Pierre-Simon Laplace, who figured out this wonderful implication of classical Newtonian mechanics, that the world is deterministic. That if you could imagine what he called a vast intelligence, and later commentators dubbed Laplace's demon, and these days you would say a super intelligent computer, that knew the position and velocity of every single thing in the universe, plus the laws of physics, you could calculate where everything would be at every point into the future. That is the sort of philosophical essence of classical mechanics. Then along comes quantum mechanics, messes everything up. This is Werner Heisenberg. It starts out not so bad. In many ways, quantum mechanics isn't any harder, in fact, is simpler in some ways than classical mechanics. Just like classical mechanics, there's a state of the system, and there's an equation that tells you how it moves. In this case, rather than a point in phase space, the state is a vector in what is called Hilbert space. Hilbert space, named after David Hilbert, is just a really big vector space. All you need to know about it is that it's the vector space where quantum mechanical states live. And then there's an equation. Instead of F equals ma, you have Schrodinger's equation, which tells you how the quantum state evolves with time. So far, so good, it's just following the same paradigm. Sadly, it ends there, the simple parts of quantum mechanics, and the difficult parts come in, because this by itself, the space of states and the equation of motion, it is claimed, are not sufficient to define a quantum mechanical system. You need to talk about what happens when you look at it. The reason why quantum mechanics is more difficult to comprehend at intuitive level than classical mechanics is because there's a whole separate set of rules for what happens when you observe systems. In classical mechanics, observations are easy. You observe the system. You could measure in principle the phase space information to arbitrary accuracy without disturbing it. Quantum mechanics comes up with this apparently weird and arbitrary set of extra rules for what happens when you observe systems. You can only observe certain things, not other things. You can't observe the whole quantum state at once. The probability of getting an outcome is not 1 or 0. In classical mechanics, if you do an accurate measurement, you're going to get the right answer. In quantum mechanics, you can be as accurate as you want. There's an absolute amount of uncertainty that you cannot possibly avoid. The rule that matters is what is called the Born rule, after physicist Max Born. The probability of getting a certain measurement outcome is what is called the wave function squared. The wave function is the way we have of thinking about these quantum states, which says to any possible measurement outcome, I assign a number, the wave function, and then I take that number squared to get the probability of getting that. And then most weird of all, after you observe it, the quantum state of the system dramatically changes. No matter how delicately you touch it, it could change by an enormous amount. It could become an almost completely independent thing. So as you might expect, this is weird. In fact, I would say this is terrible. None of this really makes any sense, and yet this is what we teach you. This is what you will be taught if you haven't been taught it yet. All those rules that I just gave you, we say this with no apparent embarrassment and expect you to repeat them in the right circumstances. But you should be asking yourself, what do you mean by an observation? What is that supposed to mean? Do I need to be awake to do an observation? Could a cat do an observation? What about a video camera? Does that count? When does it occur? Like in science and theories, we tend to think that our specification should be very precise about when things happen, not just, well, I looked at it, and this is what's going to happen next. What divides the observer, who purportedly lives in the classical world, from the quantum system that they're looking at? Why are there probabilities at all? So all of these questions get grouped up into what is called the measurement problem of quantum mechanics. And there's a whole field of study devoted to it called interpretations of quantum mechanics. There's no field of study called interpretations of classical mechanics. It's just too obvious. But quantum mechanics somehow needs to be interpreted. Now, physicists have noted this, and so you can hear people like Richard Feynman, my predecessor at Caltech. I actually sit at the same desk at Caltech that Richard Feynman used to sit at. That's my claim to fame. The desk goes to the most senior theoretical physicist at Caltech who is not senior enough to get a brand new desk when they arrive. So Feynman famously said, I think I can safely say that nobody understands quantum mechanics. And it's true, at least if you interpret understand as not only understand, but everyone else agrees that you understand. It's possible that I understand quantum mechanics. It's possible that you do, but there's no understanding that everyone says is the right one. That's fine. It's good to not understand things. That's how physics makes progress. You don't understand something, you think about it, you get better and better at it. That's okay. The problem is, what have we as a community done in the face of the fact that we don't understand quantum mechanics? You might think that we would say, well, quantum mechanics is the foundational principle of the universe. Understanding is the most important thing. Therefore, people who study interpretations of quantum mechanics should be the most sought-after faculty member researchers in all the physics departments. They should get all the prizes, they should be sought after and stolen from university to university, and none of that is true. In fact, if you study foundations of quantum mechanics, you will never get a job in a real physics department. You will soon switch to philosophy and rethink your life choices. In other words, there's a parable that Aesop tells of the fox and the grapes, right? The fox wants the grapes, he jumps up over and over again, he realizes he can't reach the grapes. Eventually he says to himself, you know what, I didn't want those grapes anyway. They were probably sour. So in case the metaphor is not completely clear, The fox represents physicists. The trace represents understanding quantum mechanics, okay? We tried to do it, it didn't work, so now we say, honestly, like, understanding quantum mechanics is bad. You shouldn't try. That's what we teach our students. And I want to undo that. I think we can do better. I actually think it's important to try to understand quantum mechanics. Of course, we don't have time to go through all of the possible ways of understanding it, so this is my favorite one, which I'll just get the sales pitch for. It comes from Hugh Everett. In case you were thinking that I might be exaggerating about the response to trying to understand quantum mechanics, Everett tried to understand it. He wrote his PhD thesis and he was kicked out of the field immediately. He went on to work on game theory and nuclear war and things like that. But here's his PhD thesis in Princeton, 1957, the relative state formulation of quantum mechanics. And basically, what Everett says is, you know what? Secretly, we didn't need any of those rules that never made sense about what qualifies as an observation in quantum mechanics. Secretly, if you give me the quantum state and the equation of motion, that's all you need, just like in classical mechanics. The fact that when you observe something, you only predict probabilities, the fact that wave functions collapse, all of these are only apparent. They're not actually real. They're approximations, just like when you had the air in this room, we approximate it as a gas or a fluid, even though we know it's really made of atoms and molecules. Everett says you can derive collapse and probability and all that stuff. The price you pay is that when you make an observation of a quantum system and you get an answer, the electron is spinning clockwise. There was, in the old-fashioned way of thinking, a probability you would have gotten the answer the electron was spinning counterclockwise. And Everett says that, in fact, both possibilities are realized in the universe. The universe branches from before you made the observation, one universe, to after you made it. There are now two universes, two worlds. One in which the electron is spinning clockwise and you saw it spinning clockwise, the other one of which the electron was spinning counterclockwise and that's what you saw. But these two worlds don't interact with each other. You cannot talk to each other. They're separate from each other for the rest of all time. Now, if you don't have a physics lab handy, there is an app for your iPhone called Universe Splitter that you can download, and if you have a difficult question, like, should I ask this guy out or not? You can just ask the iPhone, and there'll be a branch of the wave function where it says, yes, you should ask him out. And another branch that says, no, don't do that. And then if you do what the phone says, there will be a reality in which either one actually came true. That is what Everett asks you to buy. And I'm going to try to say it was the right thing to do. So in other words, here's the list in slightly more formal terms of rules for quantum mechanics that you will be taught in your textbook. There's a Hilbert space, a space of states. There's Schrödinger's equation, which tells you how quantum states evolve. There are these weird rules that involve words like eigenvalues and eigenvectors and collapse and probability, etc. And Everett says, nope, all I need is the first two. That's it. There isn't anything else. I can derive everything else just from the first two, as long as you let me believe in separate worlds. So how does that work? Well, there's only one possible thought experiment to talk about when we talk about quantum mechanics. It involves a cat in a box. And the usual way, this is Schrödinger's cat, the usual way it's discussed is you have a radioactive source with a Geiger counter. So you have a little counter that can click when the radioactive decay happens. And quantum mechanics says there's a probability per unit time that decay will happen. So there's a quantum mechanical wave function amplitude that says the Geiger counter will click, a probability associated with it not clicking. And if you believe the formalism of quantum mechanics, the hammer, which you set up to move when the Geiger counter clicks, will come down and smash a vial of cyanide poison, which in my mind I think we should replace with sleeping gas. There's no reason to kill the cat. There's history in physics of very violent thought experiments. We should be able to do better than that. My colleague Jim Hartle actually got to have dinner with Erica Schrödinger, Erwin Schrödinger's daughter, and Erica said, I think my father just didn't like it. So physics history is me. But Schrödinger's point was that when you open the box, you never see a superposition of an alive cat or a dead cat. If you believe the formalism of quantum mechanics, as Schrödinger himself wrote down Schrödinger's equation, the prediction is that just as the Geiger counter is in a superposition of having click and not click, the cat is also in a superposition of being awake and being asleep. But when you open the box, you never see cats in superpositions of being awake or being asleep. You see them either awake or asleep. So if you were a classical physicist, you would say what could be inside the box is a cat either awake or asleep. If you're a quantum mechanical physicist, if you were Schrödinger, you should say the cat can be in a superposition of both. And the question is, can we take that seriously? Can we actually believe that that's true? And the notation I'll be using is that these square brackets are classical states, the round parentheses are quantum mechanical states. So what I want to do is sort of retrain your intuition. We think that quantum mechanics is weird or mysterious, and that's probably not a good idea because it's the way the world works, right? The world, whatever it does, can't really be that mysterious. It must be our fault that we're not understanding it correctly. So if you're trained classically first, the kinds of things you say are, when I open the box, the cat is awake or asleep, therefore, I think that cats can only be awake or asleep. Apparently, quantum mechanics says they can be in superpositions, even though I never see that. That's weird and I don't understand it. So I want to invert your intuition about this to think quantum mechanically. The weirdness doesn't completely go away. There's still work to be done. But the quantum mechanical statement is, of course, cats can be in superpositions. Because cats are quantum mechanical objects and quantum mechanics rules the world. So yes, cats can be in superpositions. That's not the weird thing. The weird thing is when you open the box, you don't see the superpositions. You see the cat either awake or asleep. Why is that? And when you start phrasing it that way, we are actually able to answer that problem, that question without too much problem. So here's how you would be taught to think about the cat in your first quantum mechanics class. This is what is called the Copenhagen Interpretation of quantum mechanics, which no one really ever knows what it means. So I like calling it the textbook interpretation of quantum mechanics because it is what we teach people. It says that you should separate the world into quantum mechanical systems that you look at and big classical observers who do the looking. In this case, our classical observer is Werner Heisenberg. Okay? So the cat, which stands in for an atom, an electron spinning, or some tiny little quantum mechanical system, that is allowed to be in a superposition, but the classical observer just sees thing or doesn't. So in the textbook interpretation, when that observation is made, when you open the box and look at the cat, the wave function collapses. So before you open the box, this is what we're told. Honestly, I'm not making this up. You're told that before you open the box, the cat was in a superposition of awake and asleep. When you open the box, you collapse the wave function of the cat. And afterward, there's either an awake cat and you saw the cat awake, or there's an asleep cat and you saw the cat asleep. There's a probability of getting one or the other. Don't ask me exactly when it happened, why it happened, what makes it happen. None of those questions are allowed. You get kicked out like you, Everett. You can't do physics anymore. Okay? Now, Everett, ManyWorlds Interpretation of quantum mechanics, says just take everything seriously as a quantum mechanical system. You are quantum mechanical, cats are quantum mechanical, atoms are quantum mechanical. That's how the world works. So everything is in parentheses here, and that's Mr. Everett over there. He is going to observe the cat. What does an observation mean? In many worlds, it's not some mystical thing that you're not allowed to ask about. It's just an interaction. There is a law of physics, a dynamical law that says what happens when systems interact with each other. It's just the Schrödinger equation. So there's a process called measurement, but it's just any other physical process. It's just running the laws of physics forward. And afterward, it is unambiguous what is predicted. What's predicted is there will be a branch of the wave function where the cat's awake and you saw it awake, in a superposition where the cat is asleep and you saw it asleep. So there's nothing mysterious about the act of observation. What's mysterious is our experience. Everett predicts that we should evolve into a superposition. We and the cat are in a superposition of seeing the cat awake and seeing the cat asleep. Why does it never feel like that to us? Why do we always think we saw one or the other? The answer lies in a process called decoherence. If you ever take a quantum mechanics course and they don't talk about decoherence, you should sue for your money back. It's the most important part of quantum mechanics. The point is that Everett says the whole world is quantum mechanical, and there's a feature of quantum mechanics that we'll get to in a little bit, but there's not separate states for this and that and the other thing. There is one quantum state for the whole universe all at once. So there's not only you and the cat, there's also the entire rest of the universe, which is called, in the technical lingo, the environment. Okay, so that's a picture of the environment. The environment is really the entire rest of the universe. And what happens is just the Schrödinger equation. There's just an equation of motion and interaction that entangles you with the cat. So there's now a branch where you see the cat awake and one where you see it asleep. But then, you and the cat interact differently with the environment, depending on whether you saw it awake or asleep, right? If the cat is in the box, the photons of light in the box or the air molecules in the box will interact differently with the cat, depending on whether it's awake or asleep. So the environment also becomes what we call entangled with the cat, the state of the cat. There is an environment that essentially monitors the cat just by having all the photons and air molecules in the box bump into it. So there's an entanglement between the cat being awake in the environment and the cat being asleep in the environment. And remember, all of this lives in a vector space. Vectors have angles between them. It's easy to show that in an incredibly short time, the environment that entangles with one part of the cat becomes orthogonal, perpendicular to the environment that entangles with the other one. So I should give you the punchline here. As a result, nothing that happens in that first term of the superposition, in the rest of the history of the universe, will ever matter for what happens over here. There's no experiment you can do in one part to ever detect the existence of the other part, because the environment is this big thing. You've spilled information out into it, you will never get it back. They are orthogonal to each other. You can't do an interference experiment to notice one part of the wave function versus the other. So Everett says, just accept it. Everett comes along and says, it's okay. Don't be bothered. There's a prediction based on Schrödinger's equation that the universe splits into two parts and they go their separate ways. We call these separate worlds. We find ourselves in one of them or the other, and that's fine. That is nothing to be upset about. They both are real. They both truly exist. So that's the bottom line. Everettian quantum mechanics, the ManyWorlds Interpretation, is just quantum states, wave functions, evolving smoothly through time, no special rules for measurement or anything like that. It's because of this phenomenon of decoherence, because there's only one quantum state for the entire universe all at once, including all the particles in the cosmic microwave background, etc., that macroscopically different quantum states will very, very quickly decohere, split into two different possibilities. And then there are two different worlds, and that's just a prediction. If you believe, if your version of quantum mechanics lets you believe that a single electron can be in a superposition of spinning clockwise and spinning counterclockwise, which it had better, then the same theory of quantum mechanics predicts that you can be in a superposition of seeing the electron spin clockwise and seeing the electron spin counterclockwise. The worlds of Everettian quantum mechanics are already there. Everett did not put in the many worlds of his interpretation. Every competing interpretation takes out the worlds. That's the goal. If you don't want to believe the many worlds interpretation, you have to change the formalism of quantum mechanics to get rid of the other worlds somehow. But Everett's point is you don't need to do that to fit the data. You can just take quantum mechanics at face value. Now there are objections to this view, of course. Some good ones, some not so good ones. First I'll give you the silly ones, because some of you might have them in mind. One of them is just there's too many universes, too many worlds. I don't like it. It makes me sad to think of all those other universes out there. This is a silly objection. The size of Hilbert space, the size of the mathematical structure you need to describe the universe, is not any bigger in Everettian quantum mechanics than in anybody else's interpretation. It's just that we actually take it seriously. We actually use it in Everett. You need to get rid of the other worlds if you don't like them. The other silly objection is that this is unfalsifiable. It cannot possibly be tested, the existence of all these other worlds. Of course, it could, in principle, be tested and falsified. You just need to undecohere another branch of the wave function, to recohere the branch of the wave function. That is roughly as difficult as taking a spoon into mixed cream and coffee and unmixing them by moving your spoon. It's just exponentially unlikely. If you have an alternative to Everett, then somehow that recoherence would be impossible, and that should be experimentally detectable. There are very respectable alternatives to the ManyWorlds interpretation, and they do predict experimentally accessible differences to what Everett said. The program of testing the foundation of quantum mechanics experimentally is going on. So to say that this is untestable is just a miscomprehension. So those are the silly objections. There are also good objections, and these are not really objections because I think that the Everettian theory is the right one. What I mean is there are unanswered questions. They're good questions that we need to address as working physicists. And this is the one I want to move to in the second part of the talk here. How do we connect these beautiful equations, Schrödinger's equation and so forth, to reality? And actually, I can be honest, this is a question that many people don't even realize is a question. We kind of take for granted what the answer is, because we access reality ourselves in a certain way. We look at things, there's a table, there's a floor, etc. We think they're real, we put them into our equations. Here's the problem. Classically, that makes perfect sense, because in classical mechanics, every little part of the universe has its own state. What is the table doing? What is the floor doing? What is the laser pointer doing? Etc. Quantum mechanically, that's not true anymore. In classical mechanics, you have these positions and momenta for all these different particles. Quantum mechanically, all you have is one big wave function. The wave function of the universe. Whether you like to call it that or not, that's what quantum mechanics says exists. And it's a vector in a really, really high-dimensional vector space. Maybe an infinite-dimensional vector space, but it doesn't matter. The point is that vector spaces are boring. It doesn't really matter what's going on at any different point in a vector space. There's just a bunch of arrows pointing in different directions. They all look the same. How in the world can you look at a vector in a vector space and go, aha, that's describing a set of coupled simple harmonic oscillators? Or, oh, that's clearly the standard model of particle physics there, or that's quantum gravity or something like that. How do you connect this abstract mathematical formalism to the actual world that we see? So we're shifting gears a little bit now. It's going to look a little bit more like physics, okay? So here's the reason why we don't even think about this problem as much as we should. Because you and I are classical creatures. We think classically, we think of ourselves as classical things. Therefore, when we make quantum theories of the world, we generally do it by starting with a classical theory and quantizing it, applying the rules of quantum mechanics. So we start with some, let's say, one particle on the line as a position x. And one way of quantizing it is to promote that configuration space, x, the location of the particle, to a wave function. The wave function is just, for every possible position, you assign a complex number. That's the amplitude of the wave function. And you square that amplitude to get the probability, okay? So you imagine the space of all possible configurations. To every such thing, assign a complex number. That's the wave function. The probability is the wave function squared. That's how you go from classical mechanics to quantum mechanics. The problem, as we've said, is once you have made that wave function, it's now a vector. It's an infinite dimensional vector in this case. But it's a vector. How do you know where it came from? You can start with a classical system and make it into a function which is a vector. If someone just told you a vector, how do you know where it came from in terms of its classical origins? Nature, presumably, does not start with a classical system and quantize it. Nature just is quantum mechanical from the beginning. And this issue becomes especially sharp when we think about quantum gravity. Space-time itself. Einstein, in fact, slightly over 100 years ago, suggested that what you and I think of as gravity, literally things being pulled down toward the Earth, is actually a manifestation of the curvature of space and time. That's what gravity is. There's a picture of Einstein when he was young. Like, no one ever wants to show you pictures of Einstein when he was young. They like him when he was older and had the puffy hair or whatever. But when he was young and making up the theory of relativity, he was a sharp-dressed young man. Somebody was combing in his hair. I don't know exactly how. But general relativity is a classical theory. Of course, we have space-time and its curve and so forth, but there's nothing to stop you in principle from observing anything you want about space-time with arbitrary accuracy. How do we apply the rules of quantum mechanics to such a system? How do we quantize space-time itself? So, two problems. One is, how do you go from a classical system, how do you go from a quantum system to its classical precursor? The second is how do you quantize gravity? I'm going to suggest that the problems cancel themselves out, or at least they solve each other if you find a solution to one of them. That is to say, the usual thing we do is to quantize gravity. You start with general relativity, or string theory, or loop quantum gravity, something like that. Apply the rules of quantum mechanics to it. That's not what nature does. So what I'm going to suggest is start with quantum mechanics. What I mean by that is not some configuration space that makes a wave function, just start with a vector in Hilbert space. That's what a quantum mechanical state really is. It has some Schrodinger's equation that tells us how it moves. Given that wave function, that vector, and that Schrodinger's equation, can I extract space-time from it? So rather than quantizing gravity, can I find gravity, a curved spatial geometry responding to energy and momentum, by thinking carefully about quantum mechanics? So the secret will be entanglement. Remember, we mentioned this very, very quickly when we talked about the Everett interpretation. In Everett, when you measure something, what happens is you're a quantum mechanical system just like the cat is. So the process of measurement isn't some mystical collapse process, it's just smooth evolution. But under that evolution, you become entangled with the cat. So what does that mean is that because in quantum mechanics, individual subsystems don't have their own states, they are all part of one big wave function of the universe. And that wave function assigns a probability to different things. Let's say you ask, what is the probability that the cat is awake in this particular wave function? Well, that's going to be correlated with the probability that you saw the cat awake. They're going to be the same, right? The probability in this wave function that the cat was awake but you saw it asleep is 0. Without observing you, but observing the cat is awake or asleep, I know what you saw. That's entanglement. The state of you, the observer, is entangled with the state of the cat. It's a fundamental quantum mechanical feature. There are things that are true about subsystems that you can't know or describe just by thinking about the subsystem all by itself. It is necessarily entangled with the rest of the world. By the way, you can't use this entanglement to send signals faster than the speed of light, or go back in time or anything like that. Sorry. That is true. So, where entanglement becomes important, what I want to claim is that by thinking about entanglement in quantum mechanical states, we can actually, by making lots of assumptions, this is all very, very tentative, work in progress stuff that might all go away someday. But we're optimistic that we can build up space-time out of quantum entanglement. And to get a feeling of how to do that, let's start with something we do understand, which is quantum field theory. Quantum field theory is generally presented as being in between quantum mechanics and quantum gravity. But in fact, quantum field theory is just a particular quantum mechanical theory. When you're taught quantum mechanics, you're either taught about a particle moving in a potential, then you get a wave function psi of x, or maybe you're taught about a qubit that could be up or down, an electron spinning clockwise or counterclockwise. What quantum field theory says is that we start with a classical theory of fields. Right? Everyone at King's College should be very, very happy with fields because Maxwell invented Maxwell's equations right over there, right? The electromagnetic field is the best example that we have of a field. It's the opposite of a particle. A particle has a location in space. A field is everywhere with a value at every point, okay? So in quantum field theory, there's a classical field with a value at every point. The configuration space is the space of all possible field values all throughout the universe. Not the value at every one point, but the field configuration, like one thing the field could be doing is one point in configuration space. A different thing the field could be doing is another point. There's an infinite number of points. And quantum field theory says that to every one of those points, we assign a complex number of the wave function. The square of that number is the probability of seeing the field in that configuration. So that is quantum field theory. It's just a version of quantum mechanics where instead of particles, you have fields. This seems to be how the world works. This is the theory that predicts the Higgs boson and all those other wonderful things we discussed. You might ask, well, how come we call it particle physics? If there are no particles, there are only fields, okay? So in quantum field theory, it's not just the gravitational field, the electromagnetic field, etc. Every particle you've ever heard of is a vibration in some quantized field. There's an electron field, a muon field, a muon neutrino field, an up-quark field, etc. They're all fields one way or the other. The way that we get particles from them is actually a lot of fun. So, well, it's a lot of fun if you're a big fan of Fourier transforms. Are we all big fans of Fourier transforms? I hope we will. You will be if you're not quite yet. The point of a Fourier transform is you take a function, like the red thing on the left, which is sort of a wave packet, right? It's almost zero, far away, and it vibrates for a while, and zero again. Fourier analysis says we can decompose that function as a sum of sine and cosine waves. There's an infinite number of them to make it happen, but you can arrange all the sines and cosines so they cancel out far away, and they give you the fluctuations inside. So you can just rewrite the function you had in terms of plane waves, as they are called. And then what field theory says is you can quantize the plane waves. These are what are called the modes of the quantum field. And the miracle is, I know I'm going fast, so I hope you're all taking notes. This will be on the test. But there's a lot of stuff in here, but just believe me, because I'm fast. So every mode of the quantum field is all by itself has exactly the same physics as a simple harmonic oscillator, as a pendulum rocking back and forth, or a ball on a spring pushing it back and forth. If we take your quantum mechanics classes, one of the first things they will do is quantize the simple harmonic oscillator. And what you'll find is that the energy that an oscillator can have becomes quantized, just like the energy that an electron can have in an atom. A harmonic oscillator is the simplest possible thing to study. It has energy levels in quantum mechanics that are separated by exactly equal amounts. So there can be 0 excitations of the oscillator, 1 excitation, 2 excitations, etc. What quantum field theory says is that every mode, every fixed wavelength plane wave of a quantum field acts exactly like a simple harmonic oscillator, which means in particular it can have 0 excitations, it can have 1, it can have 2, etc. And those excitations are what you and I see as particles. That if you take a field and you quantize it, you see particles. So the motto of quantum field theory is that the world is made of fields. What you see when you look at it are particles. That's where quantum mechanics works its magic. And it's not just a little mathematical trick. The world is different in quantum field theory than in ordinary point particle mechanics or point particle quantum mechanics. So in particular, empty space is alive in quantum field theory. Empty space is doing really interesting things. It's complicated and busy, okay? If you think about point particles, even in quantum mechanics, you think about 2 particles in a big room. You say, well, the things in the room are the particles. And in between them is empty space, but there's really nothing there. That should kind of bother you, right? It bothered Isaac Newton a lot. Like, what do you mean there's nothing there? How does there a distance between 2 things if there's nothing there? Okay? Mathematically, you can describe it, but there's some conceptual problem there. In quantum field theory, the problem is solved. In quantum field theory, there's something everywhere. You can imagine dividing space into little tiny regions, and in every region there's a little quantum field oscillating up and down. And when you say there are particles, that just means that in those regions there's one excited oscillator rather than an oscillator in its vacuum state. Okay? So quantum field theory says there's a lot more stuff going on in this room than you might have thought. It's not just the atoms and the photons and so forth. Every point in space has all of these quantum field theory modes with different wavelengths vibrating to beat the band. They might be vibrating only a little bit if they're in their vacuum state. Excite them a little bit and you see some particles. Okay? So just to quantify this, I found a photograph of a famous British citizen. And let's count the number of degrees of freedom in a person versus if you believe in particles versus if you believe in fields. So very roughly speaking, the number of degrees of freedom in a person is just, or a Time Lord, just the number of particles in them, roughly 10 to the 28 degrees of freedom, you would call them. What does that mean by a degree of freedom? I mean, you tell me where the locations of the particles are and I can reconstruct the system. But in quantum field theory, if I put a box around the person, let's say 2 cubic meter box, and I count how many quantum field theory modes there are inside the box, technically the answer is infinity. because there's modes at every wavelength and the wavelengths get infinitely small. But the typical thing we do is to cut off that smallness. We say there's the Planck length, which is the smallest length we should be thinking about. And if we don't include modes below that length, the number of degrees of freedom is 10 to the 105 inside that box. So there's enormously more degrees of freedom in empty space around the person than there is in the person themselves. You and I, the Earth, the Sun, we are minor perturbations on the reality beneath us, the substrate that is quantum field, okay? And guess what? All of these degrees of freedom are highly entangled with each other. So there's a lot going on, even in empty space. You have a region of space divided up into little subregions, and you say, what is the quantum entanglement between the quantum fields in these subregions? The answer is, there's a lot. But it's not just that there's a lot, there's structure to where the entanglement is. If you have two regions that are very, very close together, they are highly entangled in quantum field theories. If you have regions that are far away, they're not very entangled. The exact fall-off depends on what kind of fields you're talking about. But it is the universal feature that nearby means entangled, far away means not very entangled. Okay? All of this is just supposed to be inspiration. I didn't derive anything. I'm just telling you stories that are true in quantum field theory. But what I really care about is quantum gravity and emergent space, right? So now we're going to go from saying things that are respectable and true to making guesses that we hope we can build into a respectable theory of quantum gravity. So here's the first guess. Rather than saying there's something called distance, and the amount of entanglement between these vibrating modes fades away as the distance gets larger, flip that over. Let's say there's something called entanglement, because that is the quantum mechanical measurable thing, and define the distance as going down as entanglement goes up. Let's see if that works. Let's see if that gets us to something that we're looking for. It's just a guess, or an ansatz, whatever you want to call it. So the picture we have is this. Quantum states are vectors in some big vector space, okay? There's a way of making big vectors out of little vectors called the tensor product. We're not going to go into the details. I wrote a book on general relativity that explains it all. You can buy it right now on Amazon if you want to. So you can take this big vector space, this Hilbert space where the quantum states live. You can think of it as the product of many little factors, which roughly speaking say what is happening in this region of space, what's happening in this region of space, etc. In the right kind of quantum state, these factors are going to be very entangled with some nearby one. Like, I need to say this carefully. Some factors of Hilbert space will be highly entangled with some other factors, but almost not entangled at all with other factors. So you get a graph, and the lines on the graph, the edges, are weighted by how much entanglement there is. And if you pick the right kind of quantum state, this graph will fit together to define a geometry. Depending on what kind of state you pick, it'll be a one-dimensional geometry or a two-dimensional geometry, etc. A generic state won't define any geometry at all, but a very special, carefully constructed state will pick out something that you and I would recognize as space, as a discretized approximation to a smooth manifold with a certain number of dimensions. So the claim is that by taking entanglement as a proxy for distance, the right kinds of quantum states naturally look like emergent space, the Euclidean space that you and I know and live in. In this picture, everything that is not the words quantum state or Hilbert space are useful approximations, or what we more technically call emergent phenomena. Like we said, the fluid description of the air in this room. Okay? So when you talk about space, field, particles, forces, matter, energy, these are all emergent out of the underlying quantum state. So how would we turn this idea into some equations? This is John von Neumann, a brilliant Hungarian physicist and mathematician, who told us that the word we should use when we talk about entanglement is actually entropy. Entropy existed for a long time before then. Professor Maxwell talked about entropy, Boltzmann and his friends back in the 1800s. And one way of thinking about entropy in the classical statistical mechanics sense is it's a measure of what you don't know about a system. If you know the exact microstate of every single atom in the room, then in some sense your entropy is very low. Entropy is a measure of information that you don't have. if you don't know the state of all the atoms in the room, the entropy is very high. But what one to realize is that if you have subsystems of a quantum system, subsystems A and B, you can know exactly the state of the combined system, A plus B. But if they're entangled, there is no such thing as the subsystem state of A and subsystem state of B. You lose some information when you forget that B exists and you're just trying to describe A. So unlike statistical mechanics a la Boltzmann or Gibbs, where in some sense entropy is subjective, it depends on what you know, but Neumann says in quantum mechanics there's an objective notion of entropy that tells you how much entanglement there is, how much information you're missing in one system if you forget that another system exists. So if the entropy of a system in quantum mechanics is high, you know it's entangled with something else. We have an example of a quantum mechanical system with very high entropy, namely black holes. I think that Eugene Lim gave you a lecture on black hole entropy last year. Years ago, you're too young to have seen it. It was awesome. But these guys, Stephen Hawking and Jacob Bekenstein, back in the 1970s, argued that black holes, despite just sitting there and classically being quiet, actually have entropy. There's a temperature and the whole bit. They really fit into the thermodynamic paradigm very well. The interesting thing is, the entropy of a black hole is not proportional to its volume inside, but rather the area of the event horizon. Okay? This seemed at the time to be something weird about quantum gravity. Today we know that it actually makes sense. Think about it in terms of entanglement. If you have degrees of freedom that are just on the other side of the horizon from each other, they can be highly entangled and contribute to the entropy. If you have degrees of freedom, one is deep inside the black hole and one is very far away, they will not contribute at all because they're not entangled. So, of course, it's actually very natural for the entropy of a quantum system to be proportional to the area of the boundary around it. So let's take that as inspiration and make another guess. Let's guess that this is a general feature of emergent space, or emergent spacetime. Let's say if you have some little quantum mechanical degrees of freedom, and you draw a circle or any other surface around some of them, so the surface is sigma, so A is the inside of sigma, B is the outside, you can calculate the entropy of A. That's a function of the surface that you drew sigma. And let's say that we're going to define the area of sigma as the entropy of the region A that it encloses. Okay? This is completely compatible with what we know about quantum field theory, but we're making a leap by guessing that this is going to be true in quantum gravity as well. If you did that for every surface you could imagine drawing, that would determine the geometry of space just like distances would. So we put together some steps in a project. We have the following connections to each other. Geometry is defined by entanglement, right? We're saying that the area of the surface with the distance between 2 points is defined by the entanglement between quantum degrees of freedom. And we also said we can measure entanglement by calculating entropy. Okay? So if you treat these arrows as equal signs, geometry is related to entropy. If only we could relate entropy to energy, then we would have a relationship between energy and geometry, and it would start sounding like gravity. It would start sounding like mass creates gravity, right? And we do. There is a rule called the entanglement first law that says in a quantum system, if you change it a little bit, if you perturb it, its change in entropy is proportional to the change in a certain kind of energy called the modular energy. But it's not surprising. What it's saying is, if you think about the quantum field theory and all these degrees of freedom, when they relax, when they go down to their low energy state, they become highly entangled with each other. In the vacuum, there's a lot of entanglement. And if you destroy that entanglement, you create more energy. It costs energy to destroy entanglement. So there is very, very naturally a relationship between entropy and energy. You put that together with the other things on the previous slide, there's a relationship between geometry and energy. If you think of these different parts, these degrees of freedom in Hilbert space, you change their entanglement, you change the distance between them, that's curvature in the manifold that you're looking at. So, guess what? We've invented something called gravity, or general relativity. We're saying that there's a relationship in the emergent classical description of this quantum mechanical state between geometry and energy, and that's exactly, in fancier notation, what Albert Einstein proposed 102 years ago in Einstein's equation. The curvature of space-time on the left is driven by energy and heat and stress and momentum and so forth on the right. This is Einstein's geometrical understanding of gravity. Gravity is just how space-time responds to energy and momentum by becoming curved. So the program we have, the aspiration, again, we're not done yet. Okay, this is research, ongoing, we've crossed our fingers a lot, we don't know all the answers yet, but the program that we're trying to fill in is pretty clear. You start with a quantum wave function. You don't start with some classical system and quantize it, you start with a wave function living in Hilbert space. You say that the entanglement between different parts of that wave function can be interpreted geometrically, can be interpreted as a function of area or distance and so forth. And then you naturally notice that if you go through how that entanglement lives in space-time, you get in the classical limit something that looks like Albert Einstein's field equations for the general theory of relativity. This is the most possible optimistic spin you could put on this. There are many problems. There are many issues here that we've not yet figured out. But it is at least conceivable that the world could actually work this way, right? That quantum mechanics doesn't really have gravity as its enemy. That if you look carefully enough at quantum mechanics, gravity comes out very, very naturally. And that better be true because we think that quantum mechanics is how the world really works. Thank you very much.